So now we're going to learn about functional groups. So functional groups are actually what really determine the overall chemistry of this or of whatever organic molecule that you're looking at. The functional groups really affect those overall properties. And the way we represent these groups in compounds is by just writing in an R sometimes. So this R represents the alkyl portion. So whenever we're trying to just represent alcohols as a whole, we could write R, which is the part that has the C's and H's, the hydrocarbon part, and then the functional group will be bonded to that. So this just represents like groups. So anytime you see R, that's the hydrocarbon part. So we're starting off with the functional groups, which you have already heard about. And these are alkene and alkyne. So these are considered as functional groups just because they do change overall properties. And then we go into, so these, we learned about them, how this double bond, we can have geometric isomers because those double bonds don't rotate. And then we learned about this triple bond. Now, the first, true functional group that is different from these two is the alcohol group. And the suffix for it is OL, all. The group itself is an OH group. So you can see right there how there's, the organic part, the hydrocarbon part, and then we have an OH group bonded to that. The simplest type of alcohol is actually called methanol. So it has meth, one carbon, that's what we mean by meth, and then the ol part, which is the alcohol part. Next we have ether. Ether is whenever we have an alkyl group, so R, O, R. So I'm going to denote these with R so that you can get kind of a better idea about how that is the hydrocarbon part and where the functional group part comes in. So ROR, meaning you can have an alkyl group, whatever it is, it can be whatever variety on one side and then an oxygen in the center and then an alkyl group on the other, and this is called an ether. The way that you end these for the suffix is most likely it'll just be ane, and I'm not sure why the textbook has so many mistakes in these tables. I'm very sorry about that, but the ending will most likely be ane, and somewhere in there you will see oxy. So these names are a little bit more complicated. We didn't learn how to name that. You're not going to learn how to name that. Maybe when you get to organic you will. But you'll see that a lot of the common names that we use for these compounds, you just say whatever the alkyl groups are, and then you end it with actually ether. Next we have alkyl halides or haloalkanes, however it is that they are being referred to. Typically we'll end it with "ide" to refer to that halide. So you will have an alkyl group, and then this X right here represents a halogen. Remember, halogens are the group right next, they are to the left of the noble gases. So here are the noble gases, and then right next to it are the halogens. Halogens include chlorine, bromine, fluorine, all of those. So here, for example, we have chloromethane. It can also be called methyl chloride, so that's where that "ide" ending comes in. And then we have amines. So amines have an alkyl group, obviously, and then a nitrogen somewhere in there. So for example, here we have ethyl, right? A two-carbon chain, and then we have an amine part, the NH2 part. So we have ethylamine. Next, we have aldehyde and aldehyde. So you've probably heard the most common one that I had ever heard in my life, before chemistry, before college, I had always heard formaldehyde, right? And I don't remember exactly where, but I would hear it like every once in a while on TV shows and stuff. Formaldehyde is that horrible smell that you smell whenever, for example, if you have ever dissected an animal in any biology class in high school or middle school, that is that horrible smell. So it's a preservative usually. Obviously, the amount always depends. But anyway, that's a very specific type of aldehyde. There are many types of compounds that you can call them aldehyde just because it even has this, little group in it. It may be a completely, different type of compound over here, but it has one little group there that's an aldehyde group, so you end up calling it an aldehyde. But anyway, I digress. So an aldehyde, the typical ending is Al. So for alcohol, it's Ol. For aldehyde, it's Al. And you can see here, right, ethanol instead of ethanol. So it has an aldehyde group right here. Ketone, you have a carbon double bonded to an oxygen. You can see it here. That's the ketone part. Oops, that's what I was supposed to. And an obvious example or a very easy example is acetone. So acetone, you use it to take off nail polish, sometimes to dissolve things or to clean things. And then we have carboxylic acid. Carboxylic acid, as its name suggests, it does have acidic properties. So because it has that hydrogen, that proton that it can give off, it can act as an acid. So many organic compounds can or do have acidic properties because sometimes they do have that carboxylic acid functional group on it. Typically, it'll end with oic acid. So for example, ethanoic acid. And the common name is actually acetic acid, and this is vinegar. So remember, vinegar is an acid, and the actual, chemical name for the acid that makes up that part of vinegar is called acetic acid. Next, we have esters. Esters have a group that similar to ketone, where you have a carbon double bonded to an oxygen. So this part itself, a carbon double bonded to an oxygen, this part itself is called a carbonyl bond. This carbonyl bond is common within a ketone, within a carboxylic acid, within an ester, and within an amide. So these all have a carbonyl group, but they're slightly different in terms of what's right next to it, okay? So definitely notice that. So an ester has that carbonyl, and then it has an oxygen right next to it, and then another carbon after that. So an example for this is methyl acetate. Acetates, very common ones that I see, is in nail polish. So that very strong nail polish smell is typically butyl and ethyl acetate, if you were ever curious. And finally, we have amides. So this again has a carbonyl group, and then it has a nitrogen right next to it. And you typically end the name with amide. So just to go into a little bit of detail into most of these and kind of give you more background information so you can kind of connect it to your daily life. So alcohols, they contain that OH group, one or more of them. It's called a hydroxyl group or an alcohol group. They are named after their parent hydrocarbon, and then the suffix, you change it to -al, as we saw in those examples. So for example, here we have 2-propanol. So the 2-propane part comes from this, right? The 2 is referencing where the alcohol group is bonded to on the chain, and then the OL at the end is referencing that you have an alcohol group. And you could say the same thing about, you could break the rest of these down like that and you can figure that out. 2-propanol is actually rubbing alcohol, isopropyl alcohol. So you can see how it's a lot different from ethanol. Ethanol is this. So there's a reason you're not supposed to consume isopropanol thinking that it will do the same effects to your body as ethanol. Ethanol is very different in comparison to isopropanol. Do they both have the alcohol group? Yes. Are they both chemically considered alcohols? Yes, but they're not the same thing, and they are very different. And here are more examples. Obviously, they can get more complicated. So cholesterol, it has that same ending, OL. And the reason for that is because it does have that OH group within it. So obviously, very, very large alkyl part on it, or alkyl group on that attached to that OH. But at the end of the day, all these alcohols are considered alcohols because they have those OH groups. I thought this meme was funny. I have a fear of hydroxyl groups. Oh, get it? Get it? No, are you rolling your eyes at my lame jokes? It's okay, I am too. I like to throw memes in every once in a while. Sometimes I won't even like say anything about them in the videos. I'm just like silent about it, which I think is funny because it's like, is she gonna talk about it or not? So it keeps your attention. Some properties and uses of alcohol. So they're very polar, meaning they're very soluble. So think about how there's so many types of alcoholic drinks. The reason for this is because they all dissolve in water. So you have many different varieties, many different concentrations of them. So like liquor, it's a very high concentration. So it's a lot of alcohol, ethanol specifically, dissolved into water. Beer, it's less concentrated. So less ethanol dissolved into water and all those other components. Methanol, obviously not an alcohol you want to drink. Used as a fuel additive, ethanol in alcoholic beverages. Ethylene glycol is an antifreeze, also something you do not want to drink. Glycerol is something in cosmetics that softens your skin. Phenol is a type of, it can be used in making plastics and can be used as dyes. And then cholesterol, obviously, is part of your body's pathways. It's very important in membranes. So you need a certain amount of cholesterol and a type of cholesterol. Some of it is bad, right? In terms of like being healthy. Then we have ethers. Again, that's ROR. So you have some sort of hydrocarbon group, and a O in oxygen sandwiched in between. So they're not very reactive. They're typically used as solvents. This is what I was mentioning earlier, how there's functional groups containing this carbonyl group. A carbonyl group is C double bonded O. And these are all of the functional groups containing them. I think I forgot to mention aldehydes, so I'm sorry about that. But these functional groups contain that carbonyl group. So again, just some more information on each functional group. Aldehydes, they look like this. So the most basic aldehyde is actually formaldehyde, the one that I was discussing earlier. There's ethanol, which is called acetaldehyde. Acetaldehyde, that is the molecule in your brain that gives you those horrible hangover effects. So alcohol is basically, as a byproduct, turned into acetaldehyde, and that is what gives you hangover. So ethanol, you see how it has that same eth part as ethanol. Yeah, so interesting fact, right? Ketones have two R groups attached to a carbon atom, so they have the two alkyl groups. They sandwich this carbonyl group right here. So this is acetone. That's, again, the most simple ketone there is. That's the one that you use to take off nail polish. Obviously, they can get more complicated. There's testosterone. So it has that ketone group right there. So a lot of things that, have to do with your body, or just, they have like these common names, but they also have part of it being like, it has some sort of chemical root to it, right? So testosterone, the own part is from it having a ketone group. And we know testosterone, again, is part of biochemical pathways. Specifically, it is what contributes to characteristics like a lot of hair, things like that. A lot of aldehydes are actually what make up a lot of flavor. So vanilla, cinnamon, spearmint, caraway flavors, they come from aldehydes. Ketones most likely are going to be used as solvents. So solvent is something that dissolves something a lot of compounds very well. So again, think of acetone, how it dissolves nail polishes really well, it dissolves acrylic nails really well. So the most important solvent other than water, again, is acetone, which can dissolve so many organic compounds. Then we have carboxylic acids. Like we stated earlier, they have the carbonyl group and then a hydroxyl group like right next to it. Lactic acid, this is actually the acid that builds up in your muscles and ends up causing soreness. Citric acid, this is the one in citrus fruits. And then we have many other types of acids. And remember how I mentioned that this contributes to it having acidic properties? It's a weak acid, so just keep that in mind. It's not strong acids, right? This isn't like burning up your muscles from the inside out. It just forms and it leaves you feeling sore, and you know, your body takes care of it. Then we have esters. So esters, they are special because they are very common in fruits and perfumes. So from this you can probably tell, oh, they probably smell good, and they do. So they have very strong sweet smells. So I remember in organic, when I took organic, we had to identify an unknown ester based off of its, you know, chemical properties, but also part of what we you know, observed, you know, wrote down in our observations was how it smelled. And you know, for example, you could have gotten the ester that smelled like banana, the one that contributed to banana flavor or smell, or a different one. So I remember noting that down, and that always stuck in my head, that esters smell really sweet. There's a special type of reaction, basically. I know I get into detail here, but basically there's a special type of reaction where you heat up an ester in the presence of a base and you end up making soap. So soap requires a nonpolar end and a ionic head. And this double, you know, the fact that it has nonpolar end and a polar head, this contributes it to being able to dissolve with both grease and also water. So it forms micelles, like I stated. This was back in this was back at the beginning of the semester where we learned about how soap works and detergents. Then we have nitrogen containing organic compounds. So these are your amides or your amines. And amides specifically, they have your carbonyl, and then you end up having a nitrogen group somewhere attached there. Amines by themselves, so amines are kind of like the simpler version, and then there's amides, right? So amides are these, and then amines are just whenever you have a nitrogen. Amides, you have to have that carbonyl group. So those are all the functional groups, and now we're gonna visit one last topic about why organic molecules are special, and this is chirality. So chirality is whenever you have a central atom and it has 4 different groups attached to it. So let's say this has a methyl group and then an ethyl group. So this has an ethyl group, a methyl group, a fluorine, and a chlorine attached to this central carbon. This makes that carbon chiral. Now we could have this same type of molecule, but it's mirror image. So for example, this molecule here, it has a mirror image. This mirror image is not superimposable. What superimposable means is that you can lay them on top of each other and they will line up. So for example, your hands, look at your hands. They are, you know, complete mirror images of each other, right? My pinky mirrors my other pinky. Everything. My thumb mirrors the other thumb. It's on the end of each hand, right? And when I try to lay one hand on top of the other, it's not the same. It doesn't line up, right? One thumb sticks out one way, the other thumb goes the other way. So they're not superimposable. So what this makes them is enantiomers. Sorry, I just scratched that out. This makes them enantiomers, and these are optical isomers, meaning they're isomers. Isomers just means you have the same formula and the same types of atoms, you know, same number of atoms. and then whatever descriptors in front of it. So for example, we have structure isomers that we learned about first. This is whenever you have different connections, different bonds between the atoms, right? Like different, basically, setup of how the atoms are bonded. And then we have geometric isomers, which we learned about, has to do with alkene molecules that have double bonds, right? We have those geometric isomers that have different arrangements. So you can have cis or trans isomers. And then now we are learning about optical isomers. So this is how they look visually and how they're not superimposable. So enantiomers are special because of this. They, in this special light called plane polarized light, they will rotate in different directions because of this. In your body, specifically, they are special in terms of the idea that your body can recognize different enantiomers sometimes, which is, you know, kind of scary because you could have just the different, you know, enantiomer, and it could wreak havoc on your body versus helping you. So there are certain drugs like that, that the, you know, one of the enantiomers is super helpful, one of the enantiomers is deadly, for example. So those types of properties are important. Whenever you have equal mixtures of enantiomers, it's called a racemic mixture. And yeah, this is basically what I said. Often only one enantiomer can be clinically active and the other one can be inert, meaning it doesn't do anything, or harmful. So enantiomers are important. Hopefully this illustration does help you. So they're mirror images, non-superimposable. Okay, so this is the last video that I have on organic chemistry, and you may be thinking, I still don't understand a thing. That is completely okay. So that's why I have this meme here. The first time you read about organic, you're going to feel like this. The 1,000th time, you're going to feel like this. I still feel like this sometimes. Like reading some of these things, I'm like, wait, I'm sorry, what? So, you know, don't feel like you have to learn it all at once right now. If you take organic, you will be learning about it, you know, lecture by lecture. Take it one lecture at a time. Always revisit the basics if you need to. Carbon must always have 4 bonds. If you draw carbon with 5 bonds, your instructor is going to flip, and you will get that answer wrong. So just keep those simple things in mind and revisit these videos whenever you need to. And obviously, good luck whenever you take organic, if you do take it. If you are not taking it, yay, you're done with organic. You won't have to see it again.